Okay. So, just a quick reminder of what we talked about last time. So I guess the main message of last time was sort of this three-way connection that exists between multiple objects in circuit complexity and communication complexity and proof complexity. So I guess we reviewed this Karshmer-Wigderson connection. So this showed that Boolean formulas for any Boolean function are just equivalent to, say, communication protocols for that solve a related search problem, the Karshmer-Wigderson game. And this equivalence, as we showed, is a very, very strong equivalence. Like these are really just the same object. Like mathematically, they're like the same object. Okay. And we showed that, okay, so we also discussed quite a bit about what happens when you look at the monotone case. So when this Boolean function is monotone, in the sense that it's monotone increasing. And there we showed that, I mean, people often ask, like, why do we bother studying monotone lower bounds in any case? And when you understand this connection, and when you observe that if I want to prove lower bounds for any, it turns out that proving lower bounds for any search problem at all is equivalent to proving lower bounds for monotone problems. So this means that monotone candidates are a very natural place to start, because if you wanted to prove any lower bounds at all, you have to prove any lower bounds at all, I guess. So just to remind that, so we say a function is monotone if it's monotone increasing. If x is less than y bitwise, then fx is less than f of y. Okay. So monotone Boolean formulas under this connection are going to correspond to something called the monotone Karshmer-Wigderson game, which we also saw was just equivalent to if I took any covering of rectangles at all. There's a natural search problem associated with it, which is, well, there's a lot of people. There's a natural search problem associated with it, which is just given a pair of inputs, output the name of a rectangle that you're contained in. And we showed that, in fact, any, like starting with any such rectangle cover at all, you can extract a monotone Boolean function out of it, right? So, yeah. Yeah. So, yeah, right. So, he does, yeah, he does. Yeah, so I'll give some. So Razborov like deserves credit for this observation originally, because he applied it to the disjointness matrix and used it to extract actually like a Boolean function from that, which turned out to be a variant of like set cover. But he did it just for disjointness and did this transformation, even though it obviously worked. And actually, Anna Gao showed in like slightly later proved actual like a more general translation between these two things.
But it puts the framework of the general cover problem already.
That's true. Yeah. Oh, it is. Yeah. Well, I mean, for this equivalence, she shows. So Anna's is for regular for general rectangle covers, but yeah, she shows this equivalence for sure.
Like it's a special case.
What do you mean by special case?
So I thought
I mean, Anna has a statement in her paper which says if you start with any rectangle cover, you can extract a monotone Kashmir-Wigderson game from it. Yeah. Yeah. Okay, good. Okay. So the other thing we talked about, which is the connection to proof complexity, is this notion of an L semantic proof system. Okay. So this doesn't appear anywhere in the literature as far as I can tell, something that I just introduced for the talk, but I think it succinctly describes what's going on quite nicely. So what was an L semantic proof system? Okay. So it's a very, very general way of writing down like a proof or a deductive system. So I'll write down the whole definition again because we'll use it. So you have some set U, use a fancy U, which you think of as being like a universe, just sort of some universal set. If you'd like, you can think about U as being like the set of all Boolean strings or just some product set, something like that. And then we're going to have some collection of lines. Okay, so these are just sort of functions on U, or just sort of collections of subsets of U. And we'll assume that the actual universe itself is in there.
Already by taking functions, you already say it's semantic and not syntactic.
Exactly, yeah. OK, so we'll describe a very, very general method of deductions over this. And the basic idea is the following. If you start with, like, suppose you have a set, some collection of lines, A1 up to AM in L, such that the union of the A sub i's is everything. Okay. Well, then we can write down what it means to deduce the universe from each of these guys individually. Okay. And it's a very, very general way. Okay. So an L proof of U from the A sub i's is just going to be a sequence so the last element in the sequence is going to be everything. Okay. The first elements in the sequence, I at 1 up to m, are just the A sub i's. Okay. And then for every j, which is not, like you can think of these A sub i's as being axioms. For every j that's not an axiom, the B sub j will be deduced from earlier ones. So I'm going to write it like this, but then I'll say what I mean. So B sub I and B sub k deduce B sub j. And by this, I just mean that B sub j is contained in the union of the earlier lines. Okay. So maybe I'll just record an example just so that because this is a little bit abstract. So a standard example of one of these sorts of things is like the resolution proof system. Okay. I guess you could say it's semantic, but it turns out that semantic resolution and syntactic are the same system. Okay. So for resolution, well, what do we have? Well, we start off with these axioms, which are clauses. Okay. So in general, these lines are going to correspond to, well, when we put it in this framework, it'll be the negation of clauses, so it'll be cubes. Okay. The universe is going to be sort of the full cube. Okay. And then, so remember with resolution, there's a single rule. So the lines typically are done in terms of clauses. So let me just write down a sort of a simple proof. So here's a clearly unsatisfiable formula, right? If all of these are true, so x1 is true implies x2 is true and also false, right? So the resolution rule allows you to take two clauses that overlap with a differing variable and deduce a new clause. Okay, so here's kind of a really simple proof where we're just cutting on these guys right there. So the lines of a resolution proof are clauses. They're just disjunctions of literals. And the way to make the connection with these proof systems is to associate each clause with the set of assignments that's falsified by that line, right? So with a clause, so over here a single line, which will be a cube, which will just correspond to assignments falsifying a clause in the proof. Does that make sense? So now this condition right here, this just corresponds to soundness, right? So if I have two lines, so if I have two clauses, say x1 and not x1 or x2, then the set of assignments falsifying it, well, saying that x2 is in the union of these two is just saying that the line that I deduce is in the union of the previous two lines. I'm just saying that every false assignment to the conclusion must falsify one of the premises, which is of course true if the thing is a sound proof system, right? Okay. And just for a second reminder, so another very, very interesting case of these semantic proof systems is the case where we take the universe not to be the set of Boolean strings, but in fact some product set. And then we can take the lines to be the collection of all rectangles over the product set. And then we recover exactly, turns out, communication protocols and Boolean circuits. So second example we can call, say, rectangle proofs. So now the universe is going to be just some product set, u cross v. Okay? And the set of lines are going to be combinatorial rectangles. Over u. Okay? And combinatorial rectangle, remember, just means any set of the form A cross B with A in the first, B in the second coordinate. Right? So what's kind of fascinating is that once you write down what a rectangle semantic proof is, what a rectangle proof is, you just recover exactly a communication protocol, a Boolean communication protocol, which by the Karshmer-Wegdersen connection is exactly a Boolean circuit or a Boolean formula, depending on if it's tree-like or DAG-like. Okay, so this is a theorem. We did it, say, last time. So rectangle proofs, well, I guess you could say tree-like rectangle proofs correspond to communication protocols. Which again correspond to Boolean circuits.
That's when U and V are 0 and 2.
No. In this case, this would be like the universe from some Karshmer-Wegdersen game. So this would be like F inverse 1 cross F inverse 0. And then, yeah, the axiom sets would just be like the coordinate rectangles that you get from the Karshmer-Wegdersen game. Okay. So the plan for today, in the first hour at least, is to prove is to give a result from a paper from a few years ago showing that the complexities of these two things are related. They can be related. So by what I mean by that is that you can show that any lower bound from this system can in some sense be translated into a lower bound in this system. And this is quite surprising because you shouldn't expect this to be, I don't think you should expect this to be true a priori. But once you line this up, I mean, in this language, it somehow boils down to coming up with some sort of meaningful translation from the set of cubes and Boolean strings to a reasonable product set, such that the deductions in each lines of the proofs, like the deductions in one proof corresponded to deductions in the other proof.
Probably was
Okay.
saying that the upper bound is this, the other direction is easy.
Mm-hmm.
Like from the system tree to indication protocol by splitting inputs.
Yeah, exactly.
Want to allow that.
Yeah. So this was mentioned last time, but yeah, just as Avi said, I'll mention it again. So it's kind of easy to see that if you wanted to simulate the direction in one way, it's actually very, very easy. So if I have like a resolution proof, it's very easy to come up with some rectangle system which simulates it. And how do you do that? Well, what's my product set going to be? Well, just start with your resolution proof and just take some partition of the variables. Right? So if I take a partition of the input variables, then this will partition this set into two, right? And then each clause will then naturally be partitioned into two sets. And every clause will, the set of assignments which falsify the clause naturally turns into a rectangle. And then, I mean, everything else is just very, very straightforward, right? So this direction is sort of very easy. You can easily show that lower bounds on these things for the appropriate product sets imply lower bounds on these things. So kind of the remarkable thing is that the converse can be shown to hold modulo a transformation on the proofs. Does that make sense? Okay. Okay, cool. All right. Okay, so the main theorem that I want to prove in the first hour, and I'll give most of the details, 90% of the details. It's the following. So so if we let C be an unsatisfiable KCNF, and I'll let G be a specific function. So I'm going to let G be the index function, which is quite simply defined. Oh, sorry, I shouldn't have these ends here. So it's quite simply defined. So you're given a string of m bits and a pointer into that string, and you just output whatever the one guy points at. Okay, so which is defined by g x y. I'll just write y sub x. Hopefully that's clear. Right? Just take the xth bit of whatever the yth string is. Okay. Then, so if there is a rectangle proof of a composed version of the formula. So I went over this at the end last time, but I'll recall the details in a second, but just to say it out loud. So this is just taking my unsatisfiable formula and in some sense plugging a copy of g in for every variable, okay? And then turning it into a rectangle cover in kind of a very natural way. Okay. So if there's a rectangle proof of this, of size n to the d, yep. Oh, yeah, sure. A rectangle proof of this. Yeah. Sure, yeah. I guess it would be of m to the n cross 0, 1 to the mn from this thing. Then there is a resolution proof, I guess to match terminology. Then there's a resolution proof of C, which has width D. Okay, actually width or order D. Okay. So the D in the exponent of the proof size gets translated into the width into the d of the width of the proof. And what do I mean by the width of a resolution proof? I just mean if I look at the proof, what's the number of literals in the widest clause? Okay. So something that's kind of notable here is that you might suspect at first that such a theorem would translate size to size. So if you had a resolution proof of size, if you had one of these proofs of size s, you would get one of these proofs of size s. And currently, we don't know how to do that.
But it may be true.
It may still be true. That's right.
What?
Sorry? It may be true. But at best, what we know how to do is translate width to size. Now, this isn't too much of a barrier for the lower bounds purposes because, well, for one thing, it tells you that it just suffices to prove lower bounds on resolution width to get lower bounds on DAG-like size. Yeah? What?
And isn't the size
Of the resulting proof? Yeah, that's true. Yeah. I mean, I guess in this case this is true, but the problem is that you cannot translate a proof of small size to a proof of small size, but also big width. And we know that there are lower bounds on resolution proofs that don't follow from width lower bounds, right? Directly from width lower bounds. And so, like, this isn't fully general is what I'm saying.
Quasi-polynomials is you too, right?
Say it again.
Up to quasi-polynomials. You have with low bounds, you have size low bounds.
Yeah, up to quasi-polynomials, sure, but I guess there's certain, I'm just saying that this isn't covering all regimes. Yeah.
So your rectangle proof is true.
This will be DAG-like. This is actually a DAG-like theorem. Yeah, both sides are DAG-like. Yeah. It also holds for tree-like, but yeah. Okay. Yeah. We would, I'd like to put it that we actually would really like a theorem that translates size to size, I think, because it covers some interesting cases, but maybe I could talk about that a bit offline. But is there any questions about the statement? No? Yeah, I'll describe what this is now. Yeah, good. Okay. So just a reminder about what this C composed with G of n means. Okay. Okay. So C is going to, so the thing we start with is going to be an unsatisfiable KCNF formula. And now, obviously, in order to prove such a result, we need to somehow, we're trying to translate the complexity of refuting this, which is over the universe or 1 to the n, to a universe over some product domain, right? So obviously, we need some way of translating this unsatisfiable formula into some product domain, some set of rectangles, right? And that's exactly what this is gonna do. And the way of doing it is kind of the stupidest way that you can imagine in some sense. So all you're going to do is you're going to replace every variable, which is normally over 0, 1, with a copy of this gadget, which is over a product domain. So the new product domain will just be like the product of all of these products. Okay? So intuitively, all this is obtained is it's just saying replace each variable in C with a copy of G on 2 new variables. So if I started with the variable z sub I, I'm going to replace it with 2 new variables xi and y sub I. Now, so before the axioms of, in the resolution case, well, the axioms have to be lines, so they have to be cubes, or in other words, clauses, right? So the problem is that you would like to say, initially, that the axioms here will just be like the composed thing. I take a clause and I replace each of the guys with a copy of the gadget, and then you would like to say, well, that's a rectangle. And of course, that turns out not to be the case, because if I take a clause and I just compose it with an arbitrary function, there's no reason to think that the intersection of those objects should be rectangles, right? But we can get around this in sort of a very kludgy way, which turns out to be somewhat natural. So, ugly. Okay. So, okay. So I'll sort of just do it by an example. So if we started with a clause zi or zj or not zk, then the direct translation would just turn this into xi, yi, xj, yj, or g of xk, not yk. Okay. So in the definition of a null proof, we want each of these things. We want an axiom over here, if this used to be an axiom, which is a rectangle. We would like this new thing to also be this is a cube. So we would like this new thing to also be an axiom. So we would like to be a rectangle. But it's not. But we'll just replace it with a rectangle. So the idea is basically like this. So after we do the composition, so after we replace each variable with a copy of this gadget on these new domains, x and y, so x is like m to the n, and y is going to be 0, 1 to the mn. Okay? So this is going to be something like this is going to look like the set of assignments which falsifies a clause. Right? So if I take one clause, the set of assignments which is going to falsify it after I run them over things, it's not necessarily going to be a rectangle. It's going to be some wacky object. So all we're going to do is we're going to turn it into a rectangle just by replacing this wacky object with a bunch of rectangles. So with a small number of rectangles. Okay? And the way to do this is quite simple. We're just going to enumerate. We're going to exploit the fact that each of these clauses are narrow. Like it's a k CNF. So we're going to, from now on, we're going to need to assume that this k is small. And we'll just enumerate over all possible assignments to these x sub I variables. Okay? And then let these y's run freely. Since the domain size will turn out to be small, and because the thing is narrow, this is not going to blow up. This is not going to introduce too many new rectangles.
But you didn't say how K and M affect the result. I mean, the K and M, factor in the
Yeah.
in the reduction, right?
Yes, it will.
Affect the big O's or whatever.
Yeah, this is true. It will affect the big O's. And it will affect the big O's. And something that's kind of a little bit hidden in this notation is when you translate this into like a Boolean function via the Karshmer-Wigderson game, these K's and M's really do play a big role in the number of variables in the resulting function. And so that will drastically reduce the strength of the lower bound. Okay, so for each assignment, say alpha to the x variables of, so let me just, if this is a clause C, let me just fix some notation right now and just call this thing C composed with G. Okay, so I'm going to use just, I'm not going to put a number there just so I don't have to keep track of how wide the clause is, but I'm just always going to mean just copy in fresh variables in sort of consistent ways. So for each assignment alpha to the x variables of C composed with G, okay, we get the following very natural rectangle. So if I take alpha and I plug it in, and then I just take whatever y is and I plug it in, then this is going to falsify C. And also x will be, x when I restrict it to the variables of C is just going to be equal to alpha. Okay. So this is a rectangle because the two coordinates are independent of one another, right? I'm fixing, I have one condition on the alpha which doesn't depend on the y, and another condition on the y which doesn't depend on the alpha. So this will actually be a product set. And it really does just correspond to tiling whatever this object is in a horizontal way. Okay? So when I run this transformation over all the possible assignments, how many rectangles am I going to get? Okay. So
M to the D.
right. Times the number of yeah. So m to the k for a single guy, and then times the number of clauses that are occurring. Yeah. So number of rectangles which are introduced for C is going to be at most m to the k, because k is the width and m is the size of the x. So this means that the total number of rectangles is going to be at most size of C times m to the k. Okay. And once you go back to this Karshmer-Wigderson translation, so as I said before, like these communication protocols over product sets are going to correspond to circuits. This is going to turn out to be the number of variables of the final function you get. And this m to the k factor, obviously, if we're trying to prove a fixed lower bound, as the number of variables increases, the lower bound gets worse, right? So this is going to be really the defining factor. That's the problem in our lower bound statement. So this is telling us we would like both k and m to be as small as possible. So if we could choose m in particular to be constant, we're not going to be able to do that in this theorem. But if we could choose m to be constant, then we would get an extremely tight connection. But as I stated it up here, this statement is just true, right? So if I have a rectangle proof of this size, of size n to the d, I will get a resolution proof of width order d. but there's a lot going on in this n to the d and how it relates to m and k. Right? Does that make sense? So this is like a fully parameterized result. But for the interesting parameters, we really want n and d to be quite closely related to these guys right there. Okay?
So would this have worked if you had covered this set with any collection of rectangles?
Great question. So this is a very natural way of doing it. We will end up exploiting this structure of these rectangles as well. So that's why I said earlier this isn't so arbitrary after all. Like it is really quite a natural choice. Maybe to say, like in a sentence, why this is a natural choice. Once you do this and you do the Kashmir-Wigderson conversion to a Boolean function, what you get is a very natural form of SAT. Actually, like you get sort of a monotone version of SAT. And if you start with an arbitrary way of partitioning this, I don't know of a nice way to write down what the Boolean function will look like at the end of the day. Okay. Okay, cool. So with that, let's start proving things. Okay, so I'm going to just use one statement, which I'm not going to have time to prove. And it's essentially an information theoretic statement. Okay. So this goes back to what Avi mentioned last time, that kind of the power of this whole translation is it takes a computational problem, like the problem of determining lower bounds, or a proof theoretic problem where you're thinking about proofs, and it gives you the potential of applying tools from information theory to attack it. And that's kind of the power of this whole approach. I'll say it's information theory, but I mean, it's combinatorics. Okay. So, okay. So one very important notion is going to be the notion of min entropy, which probably everybody here has at least seen the definition of before. So if x is a random variable, then the min entropy of x is just going to be the minimum over everything in the support of the log of 1 over the probability of x. So this is a measure of how random the variable is, and it's a very strong measure of how random a variable is, because if this thing is large, then we can say that this thing is sort of very, very close to uniform. Okay. Yeah, good. This is it's a lower bound on the Shannon entropy, which is standard measure from information theory. Okay. So now here's the main property of these things, which I'm not going to be able to prove, but it is going to show why this is the property about why I'm going to choose the index gadget here. Okay? And what it basically says is that the index gadget is like a good code in some sense of subcubes. So what do I mean by that? I mean, if I take a subcube and then I compose it with, suppose I take like a subcube like I did here, okay? And then I compose it with an index gadget and get an object that looks like this, okay? And now what I'm going to get here is going to be some subset, some wacky subset of x to the n cross y to the n, okay? So the coding property that the index gadget is going to give us is that even if I inflict like a large amount of damage to this subcube in terms of, to this object by blowing out a lot of what's going on the inside, by just removing maybe like arbitrary chunks. So let's say I remove like a large fraction of the y's, and I remove, enough of an x's, not so that I like I can delete an arbitrary piece of what this x to the n is going to look like inside of here, subject to keeping the min entropy high enough, then from the index gadget, the index gadget will still recover the original subcube if I apply it to every pair occurring in here. So this is kind of like saying like the pre-image of this object under the index gadget will be a subcube, even if I afflict very bad damage to what this object looks like. Okay? So the index gadget is like a very, very robust code to attack. And this is kind of the main property that is going to drive the connection between these two types of proofs. Okay? Because the intuition for this is that if you think about what a rectangle proof looks like, well, I'm going to start with rectangles, and then I'm going to be moving down along the proof. Like I'm going to be covering each step of the proof that's deduced from earlier steps. I'm going to cover this rectangle by a union of earlier rectangles, right? Because I'm starting with an arbitrary rectangle proof of this guy, this composed guy, this C composed with G to the n, it doesn't need to respect this structure, this x to the n cross y to the n structure at all. It can just completely ignore it. So in principle, the rectangles can, intersect with this product structure. It doesn't play nice. It can intersect with it in a very bad way. But since the index function is such a good code, it turns out that doesn't matter. Even after, no matter what a rectangle can do to it, it still can't delete an entire subcube away. That was a little bit vague, but that's sort of the rough idea of what's going to go on. So this coding property is going to be given by this following lemma. Okay, so, well, let me give a definition first. Okay. So a rectangle R in, say, m to the n cross 0, 1 to the mn is going to be row structured. Where row is a partial assignment to the underlying variables. Okay? If the following holds. If, okay. Okay. So I'll write R as x cross y. So first, if I look at x, and this row, if I look at its coordinates, which are in n, okay, some of these are going to be set to 0, 1. Those will be the fixed coordinates. And some of them will be set to star, which will be sort of free coordinates. Okay? So the first claim is that on the fixed coordinates, this rectangle, whatever's going to happen here is going to respect with this row. So this x will also be fixed on this row. Okay? Maybe I'll write this as the second thing. So, and furthermore, on top of being fixed, if I pick any element of this rectangle and I apply the gadget to it, if I just run it through the gadget, then I'll get some string z. Every such string will be consistent with this partial assignment. Okay? So all this is saying is that this rectangle is if I look at any pair of elements in there, it's going to be consistent with this partial assignment row locally. Okay? So this property in particular implies this property. But
is if you take a rectangle proof, arbitrary rectangle proof, and you make it to look as if it is working on the original variable. This
Yeah.
will turn it to a resolution proof. Right? So the gadget is helping you focus on the z variables, even though there are x and y variables floating around.
Yeah.
So this, whatever information theoretic lemma is going to let you translate or pick out the z variables that are actually accessed by the resolution proof from a very,
Yeah.
weird, unfriendly rectangle.
Yeah, thanks. Yeah, thanks, Avi. So just to make that clear, so it's what Avi said was just that what this lemma is going to represent is the translation from the rectangle proof to the clausal proof. So the idea is that the rectangle proof is going to be defined in terms of rectangles, and I'm going to define a structured notion of rectangle such that once you apply the gadget to it, once I apply this gadget to everything in this rectangle, what you essentially obtain is going to be a clause in the underlying proof. Okay? And these are some properties that are going to say, well, actually, these are some properties which are, let's say, loose enough to give me that, to actually sort of be able to extract a clause from this. Okay? Okay. So the first two properties say that on the fixed coordinates, x is going to be fixed and consistent with my partial assignment. The third property is going to say on the remaining coordinates, I have very high min entropy, even if I look at any projection. Okay? So if I take the free coordinates of this thing and I take any subset, so if I just take this part of the partition and I treat it as just choosing something uniformly over the guy, then the min entropy is quite large on this projection. So this is just taking x, projecting it to any subset, and I'm just saying that this has lots and lots of min entropy left. Okay. Okay, good. Maybe I'll just move that a little bit. It's going to be uniform over x sub I. And then the final property is just that y is going to be big. Okay? The intuition behind this is that if we think about what this proof is going to look like, the side of the rectangles, which are the Boolean strings, are much, much larger than this side is going to be. Right? This is going to be like 0, 1 to the m, 2 to the m times n, whereas this is going to be like m to the n. Right? So if you think about it from a communication perspective, all the communication could be practically happening on the left-hand side. And so I'm never actually going to be revealing that much information about the right-hand side. So this is like a very weak lower bound on how much information you need to keep here. Okay. So this is a lemma which looks fairly abstract.
What was the definition?
Huh? Oh, sorry. Thank you. I didn't state the lemma yet. So
Sorry, Robert, I'm confused on what xi is defined as exactly.
x sub I?
Yeah.
Yeah. Good. So xi. So I is a subset of the free coordinates, which is just a subset of the coordinates n. So xi is just the projection. So it's Yeah, so take this. So x is one of the sides of the rectangle. So this is just a subset of m to the n. So x sub I will be a subset of m to the I, just obtained by taking just take any x and x and just project it onto those coordinates. Okay?
And then you sample a random string from that, and that is your random variable.
Yeah, and that's my random variable. Just sample one uniformly at random. Yeah. Okay, cool. So I'll put the lemma over here. So the lemma is just going to codify this intuition that So the lemma is going to codify the intuition that if we think of this as being like a damaged rectangle. Oh, thank you. Thank you. 2 to the mn minus n cubed. Thanks. Yep. So if we think about this as, so what I said earlier was like, if we think about a rectangle proof as not having to respect this product structure. So we can think of this as, this is a very structured object, but we can think of this as being kind of like a damaged rectangle with respect to the product structure. So it's damaged in the sense that I could have deleted an arbitrary subset of y. And I could have I could have damaged the x side of the rectangle with respect to the product structure, modulo there being enough, modulo there being a consistency with some partial assignment and also enough min entropy left. But other than that, I can do potentially really, really bad damage. And the information theoretic lemma is just saying that the index gadget can recover that damage. It's going to ignore it, and it will still output the cube that's consistent with this partial assignment. Okay, so I'll write it down. So if x sub y satisfies these properties, if it's structured in this way, then if I apply the index gadget to it, this is if I try to start with a rectangle from a structured rectangle from this proof and turn it into a rectangle in the resolution proof, then what you will get is exactly a cube. So what you get is exactly like a line in the resolution proof. So once you have this lemma, here's what you would naively like to do. Start with your rectangle proof, right? Somehow transform all of the lines into structured rectangles, right? And then just apply this lemma to every single line, right? And then what you'll get is a bunch of cubes. Okay? So what you would need to do in order to control this is say, well, okay, I'm going to start with a rectangle proof of size n to the d. Once I transform every rectangle into these structured rectangles, I would like the whatever partial assignment that I'm consistent with to have width roughly d. And then you'd like to say, well, OK, now I'm just going to use the fact that this index gadget is a great code. It's just secretly encoding cubes to just directly extract a resolution proof from it. Does that make sense? This is not actually what we're going to do, but this is kind of the dream proof. Right? Is there any questions about that?
I might have missed something, but did you already say what exactly it was?
Sorry? I mean, it is the cube that corresponds to this partial assignment. So this is equals. So
You mean like the set of assignments of z's that are inside there is
yeah. So
the image of that is
yeah. So this is just exactly
not
equal.
saying how they're distributed. You're going to need more than this.
No, no, no. I'm saying that this is just exactly the rows.
As a set.
As a set. Yeah, as a set.
But I mean,
Oh, the distribution I don't care about. Yeah, yeah, yeah. This is just the image of this set under applying this function. Yeah. It's not complicated, I hope. Yeah. Is there any questions about that? No?
Did you say when we had to get a width, like why we extract the width proof rather than size proof?
Oh, why we do that? Or like why the proof works like that? We haven't gotten to that part yet, but yeah, it is one weakness of this argument, I guess you could say. Yeah. Yeah.
I would say not. Don't think about that now.
Okay, yeah. Okay.
I just don't understand why this would be enough.
Hmm?
Yes, I don't understand why this lemma made it this way, but I didn't think this would be enough.
Yeah. This is enough.
Really, you're going to prove
Yeah, I mean, I'm going to prove it.
No, but I mean, all the theorems state a stronger version, which is that the distribution is more.
Yeah, we don't need that for this. We don't need any control over the distribution or anything for this particular theorem. All you need is that it's just the cube. Yeah. So we will need one slightly stronger fact. So I'm going to say that not only is this actually going to code the cube. In fact, we can say there's a single input x such if I take gn and just apply it to there, then it's equal to the cube of rho.
Because it has a much stronger statement.
It is a much stronger statement, yeah.
Prove that you actually, the only way I know of is that you really need
You need some control on the distribution. Yeah, yeah, yeah. That's true. That's true. That's very true. Yeah, 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 yeah. I wanted to state it this way because I wanted to give sort of the dream proof first. Yeah. So like I said, the dream proof is not going to work. We can't just take the proof, turn them all into structured rectangles, and then apply this to just very nicely get a resolution proof at the end of the day. We'll need to do something a little bit stronger, and we'll need this stronger property in order to make it go. But yeah, I still don't think the proof is that bad. Okay, so it's 11:30 right now. Maybe you'll take a break for.
take a break whenever you like.
Okay, so maybe now's maybe a natural break point because after this we'll go into the proof.
So how long? 5 minutes? 10 minutes?
10 minutes, I guess. Yeah, or 5 minutes.
5. Yeah.
Yeah, okay, 5.
Overall strategy that breaks down.
No, this lemma we will use this lemma. The problem is that the basic problem is that I don't really know how to take just a regular rectangle proof and just make every rectangle structured. Yeah, like this just. So we're going to do the next best thing. We're going to take each rectangle in the proof and we'll break it up into a bunch of structured rectangles. Okay, and then we'll sort of keep track of a structured rectangle that we'll be sitting in this partition as we go down the proof. But there's a few technical details that we have to deal with along the way. Yeah. Sorry, what was the question?
In favor of Mika and Dima.
Yeah.
But they do manage to do this.
Yeah. That's exactly what that's what I'm going to describe. Yeah. Okay. So actually, let's make this a bit smaller. So I'll just create a little proof. So okay, cool. So here's what our rectangle proof might look like. Okay. So the leaves of this. So if we think about the proof as going bottom up from this semantic from this semantic point of view. Okay. So we'll take each of these rectangles. Okay. So like I said before, the dream proof would be to transform this into whatever, and then maybe it would miraculously turn out to be a resolution proof. This won't be the case. So what we're going to do instead is we will turn each rectangle into a collection of these structured rectangles. Okay. So by a partition scheme, so we'll just come up with some way of breaking each of these guys up into a bunch of rectangles. Maybe I could use a different color. Okay, how about red? Okay. Okay. So what we're going to want from this partition scheme is that, so maybe I'll do this in stages. So first, what we would like to say is that each of these guys in the partition is going to be structured. Okay? So turns out we won't even be able to get this. We'll only be able to do this up to some error, but maybe we can ignore the error for just a minute. Okay? So, okay, well, if this was the case, then we would still be in very good shape. Okay? And this is kind of also where we're going to end up exploiting the width part of the proof, the fact that we're just going to be lifting from width as opposed to size. Okay? So the idea is to just maintain one of these partitions along each step of the proof. Okay?
So you're confusing me with the two colors. So
Yep.
could you explain the two colors?
They're supposed to be the same color.
Oh.
People said green. People said green was it bright enough. Yeah. So I just partitioned.
Why did you partition everything instead of just the
Oh.
white part?
Okay. Fine. Sorry. Thank you. Okay. Thank you. That's a good question. Sorry. Thank you. I didn't understand the question. Okay. Yeah. So, yeah. So what we'll be doing as we go through the proof is we'll just be following what happens to a single rectangle in the proof. Okay. And then what we'll show is that under the partition scheme that we end up choosing, if I have a part in this rectangle right here, we'll be able to naturally relate the partitions going from one step to the partitions that will be in the children steps. Okay? Now, from one of these partitions in this step, we will be able to extract a clause, C, or a cube that corresponds to it. And then from the partitions in these children steps that are going to cover it, we'll be able to extract two other clauses, C1 and C2, which are the cubes. And then these things will be the underlying resolution proof. Does that make sense? So this actually, this again won't be true because this will only be possible up to some errors that we'll have to manipulate, sort of get rid of, but we'll deal with that just in a second.
And
Okay?
once you get the clauses, then if you go the other way, you will get exactly this.
Precisely, yeah, yeah. Once you get the clauses, we will just literally get a resolution proof of the underlying formula. And that's from this lemma right here, because each of these guys will be structured. The partition scheme will obey a certain kind of alignment property that says that this guy and these guys will be sort of in sync. They can correspond to a resolution step. So then applying this means we'll actually extract the clauses. And so applying it everywhere, we'll actually just get a resolution proof.
How are you choosing which rectangle in the partition to?
Yeah, that will be done sort of dynamically as we go down the partition. But if you've ever seen an argument from communication complexity, it's really kind of quite dumb. So all we're going to do is we're going to start with a rectangle we'll partition each of these like once, okay? And then what you'll be able to show is that, well, this rectangle, since this is contained in the cover of this, first of all, we'll just go to the one that contains more of the rectangle that you started with, and then just pick the partition that corresponds to this. And now, these things could overlap in an arbitrarily small way, but this is where we're going to use this stronger property that all we need is exactly one row can be extracted to a cube. We don't need it to overlap in a sufficiently large part. But I'm getting ahead of myself with that answer, so let me say now what the partitioning scheme is going to look like.
So can I just add something that might be helpful?
Sure.
Maybe it's helpful to step back and think that you have this rectangle, and the measure of information is min entropy about some subset of coordinates. So you want to know for every subset of coordinates whether you have too much information about that subset with respect to x. And if you do, then you're going to want to fix those coordinates. And that's what you fix intuitively is going to correspond to. You're going to fix those coordinates, but fix the x and y, and that's going to correspond to the clause, like knowing those variables. Does that help at all? It's not quite that easy, but that's.
Yeah, thanks. OK. So let me say what this rectangle partition scheme is. OK, well, we're going to start with an arbitrary rectangle, and we're going to want to break it up into some structured rectangles, except for maybe some things which will get thrown into like a small error bin. Okay? The way of doing this is kind of the stupidest way you can imagine. So what do I mean by that? Well, first of all, I mean, we just have to look at these properties and then try and satisfy them. So for this property, I mean, the main property that we really want to satisfy, the one that seems like the most difficult to satisfy, is coming up with one of these x's which have this uniformity property and are consistent with this guy. And the way that we'll do that is just by choosing a maximal set of coordinates that basically that violates this and throws it and throwing it out. Okay. So let me just write down the algorithm. Okay. Okay, so we'll just repeat the following. So just choose some set of coordinates which is maximal, such that x sub I has, say, this. Yeah, so the input to this is going to be, so we're going to be given a single rectangle, and then we want to output a partition of structured rectangles.
You don't want to say that R is large.
Plus error. Sorry?
You don't need to say that R is large.
As you mean in order to satisfy this property? You could output like the trivial partition if it's not large. I'm just going to state it for all R's, but yeah.
It's going to be an error part.
Yeah, if it's too small, it'll get thrown into some error. OK. So all we're going to do is we're going to pick a potential violation, pick some coordinates which violate this condition and are maximal. Okay? So since it has large min entropy, that means there must be some point that has too high a probability, too high an inverse probability, or too low a probability, so too high an inverse probability. So all we're going to do is we're going to fix those coordinates to that alpha sub I. Okay? So this relates to what Tony said about learning too much about these coordinates. As soon as this min entropy drops too low on some block, that means that we'll just fix that block to some assignment, and that is going to tell us what our partial restriction is going to be here. Okay. Then x sub so I'm just going to fix all the coordinates that violate this min entropy condition. Okay. And then finally, we'll update x to be xi. Okay. So we'll just do this until I. Only one part. Yeah, I'm going to do the second part now. Yeah, I'm going to do the second part now. So this is partitioning the x's. Now we'll partition the y's. Okay. And again, each of the y parts of the partition will be also sort of very familiar. It's very sort of in vein of what's going on. So all I'm going to do is for each of these x super i's where I've fixed these guys, I'll just run over every assignment to the y coordinates. And for each such assignment, that gives me a part for the y's. Okay? So xi from first step. Okay. And let's say for each assignment beta to the yeah, 0, 1, the I sub I. Beta is going to be I sub I equals beta. Okay, so hopefully this is pretty clear. So the first part, we just break up the x's into the parts that violate the min entropy condition. The second part, we just look at the output of what the gadget could be. We enumerate over all possible outputs to this restriction, and then we'll just take y to be anything that will output that beta if I plug in this alpha for the one side. Does that make sense? So with respect to this row structuredness, this beta will be the row for which we are structured. Does that make sense? So it's sort of a very, very direct partitioning scheme. Now, the way that I've stated it, okay, so well, now let me just say that the rectangle's output are just all of those guys, right? I'll just pair the union over I, and then for each beta, okay? So for each x of I, I'll partition y into the betas, okay? So this picture is actually kind of true to life. So the x's get partitioned first, so we get a bunch of parallel lines. And then the y's, well, I'm going to get along one partition. This will be like one beta, another beta, and so on. Does that make sense?
you have disjoint, you break X into disjoint set of.
Yep.
As it iterates, don't X1 and X2 have an intersection?
I'm going to remove, after every single guy, I'm going to remove what I took off for the first part. Yeah. Yeah. OK, good. So, yeah?
Why you can get them until the point when X is empty? Why cannot this I be empty?
Oh, why is this I going to be? Oh, well, it won't be I is empty. You should think of it as like as I start removing elements from the, as I start removing pieces from the coordinates, this condition becomes easier to satisfy, not harder, right? Because if the min entropy is high, that means the set is like almost uniform. So as I delete more and more elements from X, there's going to be less and less measure inside of X. So at the very end of the day, when X is like very, very small, it's very non-uniform, right? So the min entropy is necessarily going to be very, very low.
You don't apply it if you're already on cycle. Maybe that's
What?
You don't apply this at all if you're already on this one.
Yeah. Oh, what? No, I didn't quite understand that.
Saying that the end condition is the last piece, is the piece for the min entropy condition.
Yeah.
So you have this piece left over at the end.
Yeah. This piece left over will actually just satisfy the min entropy condition, though.
If R was the full rectangle,
Yep.
the original,
Great. Yeah.
so what happens
So,
to publishing?
so if R is the original rectangle, then we don't do anything because there's no set that satisfies this. So we just output the whole rectangle. Yeah. Thanks. That's good.
0.95 is intentionally greater than the
It's intentionally greater. Yeah, yeah, yeah. And the reason is that we'll want one extra property from that.
Sometimes a lot of times that'll happen. You just won't do anything. So that means like you haven't learned anything, so you just
Yeah, do nothing.
I is all the I is the coordinates
Yeah.
you know about is
In that case, would you do anything in the second step with the y's? Would you if you output the whole rectangle in the top set, would you do anything?
No. Yeah, yeah. Well, yeah, it's for each xi from the first step. So that's the empty set. So you would just
the whole
do
point
nothing.
of this is to like you fix on some set of coordinates that you learn too much about, and that's and you're sort of so then you're going to fix them to be some the y's or fix
Yeah.
them to be the various values.
Yeah, that's exactly right. Yeah. OK, so what I want to point out is that I'm going to output a collection of rectangles here. It's definitely a partition of the original rectangle. It's going to satisfy many of the properties here, right? Not all of them, but it will satisfy basically all of them. So every guy in here, OK, so it might not satisfy this largeness condition on the y, because near the end of the process, clearly we're not going to get much control over what y's are left over here. So this one is going to be left out. However, this uniformity condition is going to be kind of clearly true because it's baked in to the algorithm, right? If I pick a set which violates this condition, a maximal one, well then if it violated this min entropy condition after that, well then I could have just extended it by maximality to contain the other coordinates. Okay? So this step part 3, this uniformity condition, is actually going to be satisfied already, because otherwise I could have grown it in the earlier step of the partition. And this second step, whether or not all the z's, if I look at any rectangle in the output of the partition, if any z is consistent with a row, that's also satisfied, right? Because the row that I'm going to be consistent with is just this beta right here. Okay? And also, yeah. And the x on the fixed coordinates, well, this is also satisfied, right? Because when I was choosing this witness, I explicitly fixed the coordinates, which satisfied that part as well. So, in fact, this thing, it satisfies almost all, like it satisfies almost everything except for maybe this last part right here, this y. And these ones, these y's and some other, like, and then under some condition, we're not going to output an entire partitioning of things. We're going to, some of these rectangles will be relegated to error. So one of the conditions for error is if the y is too small. That's clear. The other condition for error comes from the fact that in the rectangle proof, we want to extract size down to width. So if any of these betas is too big, or sorry, if any of these I sub i's is too big, we'll throw those into error too. And that's basically going to be it. Okay. So maybe I can write down the property that you need right here. Oops. Okay, so So here's the properties of this partitioning scheme. Okay. So it's a different K. Okay. I'll just let L be a parameter. I'm going to let R be some rectangle. And let's suppose that we partition R according to the scheme over here. Okay. This is just a parameter. Just think of it as a parameter. This will be our error parameter. Okay. It's an upper bound on our error parameter, actually. Okay, then there's going to exist two sets, x error and y error. So x error is in x, y error is in y. Or let's say be super explicit, 0, 1 to the mn, and m to the n. Okay. With density, at most 2 to the minus L in x and y, respectively. Okay. So there's going to be two error sets of relatively small density. L is the error parameter, which this is an upper bound on how small an error we can afford. Okay. So first, So first of all, R sub I is going to be rho sub I structured. That we already argued is pretty clear for some rho I. Okay? And rho sub I is going to have bounded width. So the size of the fixed coordinates of rho sub I is going to be something that depends on an error parameter. Something like order of L, actually slightly better than order of L, order of L over log n. Okay? So this represents if I'm going to pick things that are too wide, like if this partitioning scheme outputs a guy which is too big, I'm just going to call it error and throw it away. Okay? So all I get left with is like the small ones. So furthermore, every subrectangle of R sub I with density bigger than a half is also rho sub I structured. Okay? So if you just pick any large enough subrectangle, this is going to represent like one step in the proof going to like a child. I'm still going to respect the structure of this partial restriction. Why should this be true? Well, I mean, this is exactly why I picked, as Vijay pointed out, this is exactly why I picked this to be a little bit bigger than what the threshold over there is, right? From the lemma, we're going to get immediately that the whole thing is rho I structured. Well, if I communicate a single bit about the rectangle, I'm not going to lower the min entropy below 0.9 times I log m, right? This is a very likely event. The probability of that event is at least a half. So I can only decrease this by 1. So it's still going to be bigger than 0.9 in particular, right? So this will also be true. Okay, so that's the first that's the first case. let's do the second case. So either this will hold, or it'll be an error rectangle. And by that I just mean it's going to be covered completely by x sub error or the y sub error. So thank you. Yeah. So if you'd like a picture, if this is the original rectangle that we're partitioning, well, the partition scheme is going to output all structured rectangles but some of these rectangles, the ones that are completely contained in these error columns, are just going to be called error and sort of thrown out. Okay? And furthermore, these error columns have relatively low density, like 2 to the minus L for L an error parameter. Okay? So the key thing in this lemma that you should pay attention to, so all of the things that I'm saying follow pretty much immediately from the partition scheme, as we just saw. Like, it's clear that everything is structured and so on. The really main takeaway from this lemma is this part right here. The fact that when I specify this error parameter, it's going to let me bound how wide the subcube, the partial restriction that I'm consistent with is. Okay? So remember, the original step was to transform a proof of size n to the d to a proof of width roughly d. This is the step that's going to allow us to do this. If I choose the error to be small enough, then this will allow us to upper bound how big the clauses in the final proof are going to be. Does that make sense? Okay.
So N will actually be d log n?
Yeah, at the end of the day, it will be. Yeah, thank you. Okay, cool. And with that, we're pretty much ready to do, now we've got everything set up, we're ready to do the whole proof. Okay. Okay, cool. So first of all, let's imagine that that there was no error case. Okay? Just to sort of make our lives easier. Right? Well, let's just imagine that this second case never actually happened. And in fact, we're just going to get an upper bound here. So yeah, I mean, this error parameter is still here. So like, let's not, obviously this is fiction, but let's just imagine that this was the case. Then I claim that the proof will go just as I described a second ago. So we'll start with the proof, with the rectangle proof. And we'll just globally apply the rectangle partition scheme. So each guy will just get partitioned. So we'll apply this algorithm to each rectangle separately. Okay. So the first one is everything. And then the next ones down will look like they'll necessarily cover it. And then maybe once we get down another step, things start to look a bit more interesting. So maybe this looks like this. And this one looks like, well, this one could go all the way over maybe. And then this one looks like this. Okay. So the first guy, well, the first guy, it's like not hard to see that nothing is going to happen, like I argued a second ago. With this algorithm, which I've unfortunately erased, you picked the thing that had the biggest, you picked any violation of this min entropy condition. For the entire rectangle, there's no violation. So this thing is row structured. And the partial restriction, which corresponds to this, is going to be the all-star restriction. Or in other words, the contradiction. Right? So if we imagine applying this transformation of g to the n to the entire rectangle, what we're going to get over here is that. OK. So now here's where it gets a bit more interesting. So now let's consider like an inductive step. So OK. So up here, what we know is that not only is this going to correspond to a cube, there's going to be a single element that corresponds to the cube. Right? So we could just pick, maybe I'll use a different color. We could just pick a single guy such that actually once I apply it just to x and everything in the y part of the partition, I'm going to get the entire cube. OK? Well, first things first, this will go to the larger of the two children. OK? So the union of these two rectangles by the proof property is going to cover the original rectangle. Okay? So we'll go to the one that covers more of the original rectangle. So in this case, it'll be this one. So we go to the larger one first. OK. Now, I'm going to imagine in my head that I have a total assignment over here that I'm trying to sort of use the proof to show that it violates one of the axioms. OK? So
Probably, I don't know, you mentioned it last week, but it's probably good to remind that the resolution proof viewed backwards, viewed top down,
is a search algorithm. Yeah, that's right. So we're going to be sort of implicitly using this this search to proof perspective. So if I take a resolution proof and I turn it upside down, well, if I start with any total assignment, then I can use the proof to locate a clause at which it's falsified. So I'm going to be using this sort of upside down connection here. So I'm going to imagine that there's a z with which I'm consistent, okay? And I'm going to use this to find a clause with which is falsified. And I'll do this by walking down this proof. And each of these leaves will correspond to one of the original input clauses. And that'll tell me what my falsified thing is. And then the width bound is going to tell me what how I'm going to do. Like that, none of my steps I'm going to choose walk through a clause that's too large. OK? All right. OK. So this x that I picked here, well, once I go to this child, if we remember that the definition of this algorithm right here, I still have it written right here. I know that each x sub I, if I look at all the y sub i's which it pairs with in the algorithm, each one is going to correspond to some partial assignment right here. Okay, so I have some sort of global assignment which I'm remembering. Okay, so if I imagine that I had some partial assignment that I'm remembering at this step, well then because this x, if I look down here, there must be some place along here, right, where in this cube, I'm going to be consistent with this partial assignment that I started with up here, right? So why is that the case? Well, that's just because of the way that I constructed these rectangles in the partition. So when I do this alignment down here, well, if I pick an x and I know that this row sub star is this row is consistent with my x sub star, well then I fixed all the y's so that I'm consistent with the beta. So one of these guys is necessarily going to be consistent with rho sub star, right? So what you can do then is you can pick out one of these rectangles, which is consistent with rho sub star. Okay, this is, sorry, I keep calling it rho star. So this is going to be consistent with rho. Okay. And now this guy, let's remember, this guy is consistent with its own assignment, which is necessarily, which is at very least we know it's consistent with rho, but it's actually going to be some different assignment, right? And it's also consistent with some other assignment beta. Okay. So in this step, I'm just going to do like the resolution step, which corresponds to going from this clause rho to the clause beta, since these two things are consistent. So if I have, I mean, initially I have the empty thing. So if I'm somewhere where I have a clause that corresponds to rho, okay? So what I can do is I can just query all the coordinates that this thing fixes, okay, according to this z, to get some larger set, and then forget everything that I don't need to remember with that. I can forget everything that's not consistent with this rectangle in order to get my beta. Okay, so after some sequence of steps, I'll go from rho to beta over here. So this is going to query the consistent coordinates of this new rectangle. Let's call it L of L. And then because L is also output by the algorithm, it's consistent with some assignment beta. And then we're going to forget the coordinates which are not in beta. Okay. So at worst, I'm going to take, I mean, the original row had width at most L over log n. The second one will have width at most L over log n. So I'm going to at most double that. So the width in the steps that are happening implicitly here is still order L over log n. Okay? Does that make sense? So this allows you to, so what have we done? Well, we've started with a structured rectangle here. It's consistent with some partial assignment. And now I know, because of this single input property and by the property of this rectangle scheme, that there must be some structured assignment down here, some structured rectangle with its partial assignment down here that's consistent with my x. So all you do is you just query everything in this new guy that's not in my original one, and forget everything that you don't need to remember from the previous step. Right? And at worst, so then once I'm done that, well, now my new structured rectangle that I'm going to be paying attention to is this one. And then I can just proceed inductively down the proof.
Why you have to argue why the width doesn't increase to the, I mean, you doubled the width?
No, I doubled the width going from here to here, but this guy, but I'm going to forget everything. And since this guy is a structured one, I know its width is at most order L.
So all partial assignments throughout as you go down will have at most d fixed variable.
Precisely. Yeah.
How do you drive conjugation from just law? Don't you need to perform some resolution step?
Right. OK, good. I mean, this was just the inductive step. Well, OK, so first of all, this is the top-down view of resolution. So this is going to correspond to a sequence of weakenings and then a sequence of queries. So you can convert that back into a resolution argument. So the question is what happens when you get to a leaf? So what happens when you get to a leaf of this proof? Well, a leaf of this proof, if we remember, corresponded to one of these rectangles in this canonical cover that I drew a while ago. So in particular, every leaf down here is going to correspond to one of my input axioms. And these input axioms look like these canonical rectangles. So a leaf is going to look like a canonical rectangle, which corresponds to a clause. So C of G of alpha and y is false, and x restricted to C is alpha. Okay. So now, what do I have here? Well, I'm going to get a partial assignment. Like, I'm going to end up at a structured rectangle in this leaf, right? And I'm going to get a partial assignment here. And this partial assignment is necessarily going to have to be consistent with this alpha. And in particular, this means it's going to have to falsify this clause. Right? So once I map this to here, I'm going to end up getting an actual assignment which falsifies the original clause.
So this
Yeah.
would have to explain why you don't think that why you're not getting the size that you want instead of the width. It's following
Why do you get size, not width?
in the beginning that you want
Yeah.
size. So maybe
So here
you're
you
getting it from you're getting the same structure.
here you do get the same structure. So you do get okay, yeah. So it's a little bit unfair to say that you don't get a width bound, that you don't get a size bound. You do get a size bound, but I do mean something a little bit more. So what I would like is a proof that says you get a resolution, like when I start with a rectangle proof, what would be nice is if you could get a resolution proof that you didn't have to have this control on the width bound. So you wouldn't go from a size n to the d to a width d necessarily. The problem is that you can do everything in width n. Okay? So that doesn't tell you at all what happens when, like this doesn't allow you to translate lower bounds back when you have no control over the width of the resulting proof. Right? But there's many cases in which we have resolution lower bounds, and the width of the proof is n, but we can still prove like good size lower bounds. But we have no way of translating those results back to this kind of setting. All we can do is we can use width lower bounds to prove size lower bounds here. So in particular, this is a notable gap in like our understanding of this, of these results. So let me just finish right here with saying what I said a second ago. So partial assignment. So every assignment in here, when I apply G to it, is going to falsify this clause. So all x, y falsify clause C when G is applied. So the corresponding leaf in the resolution proof is just going to be labeled with that clause C. Right? And you're guaranteed by the structure property that as you walk down the proof, you'll still falsify this clause here. Okay. So in my remaining 5 minutes, let me say what happens with error. Right? Because this was the case where we didn't worry about error happening at all. Okay? Now, handling the error is actually not that bad. So all we're going to do is we're going to do something which is very similar if you've ever seen the proof of the monotone circuit lower bounds for the method of approximations, where basically all we're going to do is just do exactly that. So the first thing that I'm going to do is I'll consider the proof from the bottom up, and I'll apply the partitioning scheme to each rectangle like I did. And now each rectangle is going to get some error pieces associated. Okay? And now any structured part which ends up in these error things, I'm just going to throw out, and then I'll just take the union of all the error sets as I work my way up the proof. Okay? So if I choose if the proof is size, so if the proof is size n to the d, and I choose my error to be something like 2d log n, right? Yeah. Well, then, the amount of error I'm going to introduce at each step, then error, so the total error is going to be n to the d times n to the minus 2d, which is definitely less than half, right? So that comes from the fact that these x error guys and y error guys have low density. Okay. So since this is at less than a half, and I know that I'm still structured as long as I go to a density, I mean, this is not going to damage anything in the proof. So all I can do now is I can just do everything relative to the structured rectangles that I didn't throw out, which I am now guaranteed have this width bound. Right? Does that make sense? And nothing else, yeah, so nothing else is going to be affected by throwing out these error guys anywhere in this proof. This top one's not going to have any error at all. OK. Well, this took more time than I was anticipating, unfortunately. So let me maybe finish by saying a few things that I didn't cover.
One question.
If there's any questions.
The only property
Yeah.
index that is used is this lemma.
It's this lemma, yeah. That's it. And there's a lot that's going in, that's being hidden in this, like a lot of, like this proof is not trivial by any means, but yeah. But yes, this is the only property of indexing we're using. If we,
And it could hold for a simpler function than index
yeah, absolutely, yeah, yeah.
in exactly this form.
Yep, absolutely. And yeah, that's one of the things that I'll talk about now. So some of the things that I didn't sort of get a chance to cover here. Oh yeah, why are the things small? Yeah, that comes from the requirements of the lemma. So I'm just going to throw out anything that's like smaller than this. And since the partitioning scheme is not that big, since there's not that many xi's in the partition, you can just show. Basically, the reason that this holds is that when I just greedily throw at everything that violates this, y is so large that throwing those out is still a small set. Yeah. OK. So let me just give you a maybe I'll say U cross V. I'd like to finish with like a high-level view of the relationships between these the proof systems, the ones that happens in the propositional world, where the universe is like 0, 1 to the n, and in this product world, where the universe is now U cross V for some product set. So what we've seen is that resolution in this world, where this corresponds to where the lines are cubes, this corresponds to rectangle proofs. Let me put this up here. So U cross. So, U equals U cross V. OK. And this is going to correspond to Boolean circuits. OK. But there's many other propositional proofs that you'd like to plug in here, which we would like to understand. And there's other U cross V proof systems we could plug in here that we would like to understand. So let me just write down, say, a few of them. So one example that I like a lot is the cutting planes proof system. So in this case, the lines are R linear inequalities. So what I mean by that, you take a linear inequality over R, and you just consider deductions which are sound over the integer points. OK? So when you do this correspondence, what do you get? Well, it turns out you don't get rectangle proofs anymore. You get triangle proofs. And what do I mean by that? Well, the object isn't going to look like a rectangle, but instead it's going to look like some kind of this object that I drew a second ago. So it's going to be a triangle in this sense. So a way to define this is saying that there's some way of applying numbers to each of these columns, say B1 up to BC, A1 up to AR. And you say xy is in the triangle if and only if AX is less than BY. Right? So this is no longer a rectangle proof. And there is also a natural circuit model which corresponds to this. This is the model of real circuits. And it turns out by coming up with an appropriate partition scheme for triangles and mimicking this proof, you can prove exactly this connection as well, again with the index gadget. So this allows you to prove. What's remarkable about this is that when you do this extraction process, you don't get a cutting planes proof. In fact, you still get that resolution lower bounds, width lower bounds will imply lower bounds on the sizes of these things. Okay? So this is one interesting case.
Wait, can you say that again?
Yeah.
That last thing you just said?
Yeah, sure. So there's a way to make this connection work so that not only do you need to start from a cutting planes proof in order to get this connection to go, once you run this whole proof in the right way, you can actually show that if I take an index gadget and I combine it with the thing, I'm going to get lower bounds from like a triangle proof of size n to the d will actually give me not a cutting planes proof, but even a resolution proof of width d. So resolution lower bounds will still imply lower bounds on these things.
Is it really cutting planes or like semantic?
It's semantic cutting planes. Yeah, all these proof systems are semantic. Yeah. Okay. One could go even. So in other examples which are studied a lot in the literature are these ResLin or ResCP systems. These are kind of like combining these two proof systems in a very crude way. So, well, not a crude way, a very natural way. So now you take your lines will now be a clause of linear inequalities or a clause of linear equalities. Okay? So this represents the limit of what we can actually prove lower bounds for. We don't know how to prove any size lower bounds for these things. And now you could say, okay, well, maybe if I think about resolution, resolution lower bounds and rectangle proof lower bounds, well, monotone circuit lower bounds were known around the same time resolution. So maybe you could prove lower bounds for whatever the corresponding system is in order to derive lower bounds for these systems. And it turns out that there's one system which can simulate both of these things. And this is like what you could call an equality proof. And by this I mean it's going to be in a block diagonal form. Okay. This is still semantic, yeah. So now it's going to look like this. And this is equivalent to it being to a single rectangle just being a single equality step. So you can imagine there being a single thing, and Alice and Bob communicate just by asking whether or not their two inputs are equal.
If anybody went to the talk by Danielle, this is
Yeah.
that he spent the whole time talking about.
Right, yeah.
Inequality between two.
So we know that this is like the right model in the sense that this can simulate this in many ways. Like, in fact, there's a generalization of this triangle proofs which correspond to these guys, and that correspond to this, and a generalization that corresponds to these linear systems. But it turns out that all of these can be simulated by these block DAG proofs. So this would be kind of like one of the frontiers to actually prove lower bounds for. And one thing which I also haven't mentioned, which I've done a lot of work in and has relationships to a lot of other systems. So everything that I've talked about over the past few lectures has been in terms of these semantic proof systems. So these are proof systems which look like deductions, like sort of standard textbook deduction systems. So there's also lots of proof systems which don't look like that. There's lots of ways to verify that something is a tautology. So this brings us to the realm of these like so-called static proof systems. These things are often algebraic in nature. So just to set up the dichotomy again. So one could talk about the Null-Stellensatz proof system. OK. So this is an algebraic proof system. And now it's no longer a deductive thing. But in fact, a proof just consists of, if you take your clauses and you write them as polynomials, just come up with some other polynomial p sub I such that you get exactly 1. So if we interpret truth as meaning 0, right, there cannot be a satisfying assignment to all the clauses if such a set of polynomials holds, right? Because plugging in an assignment would give me 0 equals 1. But this is not a deductive system in any way, right? It's somehow all the proof is just happening at once. So you'd like to be able to understand what's going on over here, and it turns out that there is a very natural model over here. It's the model of span programs. And just as you would expect, you don't get a deductive system right here. You get something which looks like a rectangle version of this statement. Something like that. And finally, let me just mention two other ones, which are probably familiar from optimization and other recent results. So there's generalizations of null-Stalin sets, the Shirali-Adams proof system or the sum of squares proof system. And roughly what these say, if null-Stalin set says 1 is in the ideal generated by these clauses, these two systems say -1 is in a cone that's generated by the clauses, where the definition of the cone depends on which system you're working in. And again, it's a static proof system. But again, we have very natural computational devices which correspond to them over here. It's these models of extended formulations. Or semi-definite extended formulations. Okay. And now, all of the proofs, all of the things that I've drawn on the board here, the gadgets for which we know that these connections exist, in almost all cases are the index gadget. This is essentially the index gadget. It works for the index gadget. Except for this one, where we actually know that any gadget of high enough rank works. And this is much, much stronger than what the other ones are saying, because you somehow are managing to avoid all of this other structures, all of this like information theoretic stuff in order to make this connection go through. So it's very natural to ask whether or not we can come up with a better arguments for these other systems that use different kinds of gadgets. And a key thing that works here is using a notion of duality instead of doing a simulation. So in all these other proof systems, you do a simulation argument where you start from a proof here and you simulate out a proof from here. Whereas this argument right here uses a duality theorem. So you prove first that like this gives like an object gives you an object, and then a dual object, which is a lower bound, gives you a dual object, which is a lower bound. So in these systems in particular, it'd be very natural to try and come up with similar proofs that look like that, especially in the case of SOS, where this lifting theorem is very, very weak and currently only gives something like n to the log n lower bounds. And yeah, maybe I'll stop there.